So let me introduce you. So welcome, Andrés Fernández Herrero from University of Pennsylvania. Thank you for coming here to Madrid. And he's going to talk about quantum operations on the ring of symmetric factors.
Thank you very much for the invitation. The goal of today's talk, and everything that I'm going to say is joined with Andrés Fernández. So the goal is to define a theoretic form with an invariance for the classifying stack of the general linear. So basically, I'm just going to try to explain what do I mean by this, and then kind of highlight some of the moduli theoretic properties or some of the moduli theoretic features that appear when you try to do that. So let me start by maybe recalling a bit about what is classical homomorphism theory. So this is going to be quite idiosyncratic, the idea is to count curves inside something x, and x is usually going to be a smooth projective variety. And the way in which we do this is by creating certain moduli space, by defining some moduli space. Maybe I can be a bit more precise, and I can fix the topological type of the curve. So, I can fix some element of second cohomology of x. And I can say that I want to count curves inside of x such that the push forward, or like the corresponding homology, second homology class for this curve, is going to be and then one way of doing this is using stable maps. So the idea is if there's finding many curves, well, then it makes sense to say what's the count. You just there's a finite number. Otherwise, what you do is, in many cases, there's not going to be a finite number of them, but there's going to be maybe a space, a compact space, parameterizing all curves of this given class inside of x. And what we do is we compute the volume with respect to some canonical measure. And that will kind of give us the number of curves in some sense. The bigger the volume, the more curves we have. And this moduli space is called stable maps. So we generally call it n bar n of x with curve class beta. So I'm introducing some parameters in here. And this is going to be the following. It's going to parameterize morphisms from a curve into x plus some number of markings. So some number of points inside of C, such that the following hold. First is that C joined with these markings. This is a free stable curve. So these edges mean that it is another curve connected. The markings don't intersect each other, they are distinct, and they align the smooth locus of the curve. And then the automorphisms of this morphism with the markings. Start using this notation. I find. I guess maybe I should say that the push forward of the fundamental class of the curve is just for this. By automorphisms being finite, I mean any automorphism of the curve that preserves each of the mark points and that is compatible with the morphism F. Those form a group, and that group is finite. Okay. This is the usual model of conservative stable maps. I guess I didn't say what G is. Sorry about that. So the genus of the curve is going to be the arithmetic genus, which is okay. And then the MaPhyAG. And one is that this moduli problem is represented by a dilemma for stack that is proper. So we have a compact moduli space. We can integrate some kind of homology class inside of here. There's something called a virtual fundamental class, and when we integrate that, we get a number. You can see that that's the number of curves in class beta inside of X with some given genus, maybe some mark points. The idea of the mark points is sometimes we may want to impose certain conditions, like we might want to impose that like the curve intersects at some given points certain subvarieties, and that's given by what is called inserting homology classes via the evaluation morphisms. So let me say a bit how the evaluation morphisms are going to work.
So do you want this stack to have the expected dimension 0 so that the volume is?
No, I mean it's just virtual dimension, whatever it is. I mean, I don't. So I'm not imposing that this is Calabria. So yes.
And then so the counting is just the volume, right?
Well, it's the volume with some insertions. So maybe the class doesn't have the right dimension to integrate, but I use this. So that's what I'm about to say. I can use these M markings to pull back certain homology classes via the evaluation morphisms and intersect my expected dimension so that I get a fundamental class, or so that I get a class in homology or in Chow that has dimension 0, and then I can integrate them. So if X is not Calabi-Yau, then I might want to impose in order to get like a count that makes sense. I might want to impose some incidence conditions of my curve at these markings with certain homology. So I might want to say, I want to count all of the curves that intersect this variety with like multiplicity to this subvariety.
Yeah. So just a simple example. So if X is the projective plane and genus 0 and no markings, then you have just the lines in P2, then you have to put some conditions so that you get the number, right?
That's right. Yeah. And in that case, you're thinking of like just the class with being the usual class of a line. Yeah. Okay. Now, so instead of volume, I kind of prefer coherent cohomology. So I'm going to compute indexes of K-theory classes instead. So I'm going to move away a bit from the count, and I'm going to define what are called K-theoretical multivariates. So maybe I should say that the second fact is that there is virtual structure sheet. From the fact that this is a natural quasi-smooth enhancement, And this is going to be, well, I can call it, I don't know, O and virtual. So this is I can think about this as a complex, but really I'm going to think about this as an element of the K-theory. Maybe more appropriate as to say the K-theory of the derived enhancement, but I'm going to kind of blur first. And then how do I count? Well, I might want to have some insertions. And then generally, if I want this to be something like a TQFT, I might want to have some input input evaluations and output evaluations. So what I'm going to do is I'm going to define some operations on the K-theory of X. It's going to go as follows. I'm going to take N to be the set 1 through N. And I'm going to choose some partition into 2 pieces. I'm going to use minus for the markings and plus for the outputs. Sorry, minus for the inputs, plus for the outputs. And then I have 2 evaluation morphisms. So I have this moduli space. And I have the evaluation at the minus markings. This is just going to take the morphism C to X, and it's going to evaluate it at the markings corresponding to the partition S minus. So that gives me S cardinality of S minus many points in X. And I'm also going to have the plus markings. And that's going to give me cardinality of S plus many markings. And then what I can do here is I can get an operation using the properness on K-theory of X. So what I can do is I can do a Fourier-Mukai transform. I can take the K-theory of X tensor S minus 1 times. I can view those as a class in the K-theory of X to the S minus. I'm going to pull back to the K-theory of NGM bar X beta. I'm going to tensor by this virtual structure sheet. And then using the properness, I know that the push forward of a coherence if is coherent. So the push forward of the K-theory class is going to be well defined. And I'm going to push forward using the plus evaluation markings to get something in K0 of X. And in nice situations, maybe we can split this into, I mean, in the situations that I'm going to care about, is here, you can think about this as K0 of X. Tensor X. I mean, there are ways of getting around this. So you can think about this as some kind of n-ary operations that take a tuple of classes of K-theory of X and spit out some tuples of K-theory of X. And these are going to be well behaved. There are some gluing morphisms. There are some gluing properties of this virtual structure sheet that make this kind of operation have a lot of recursive properties. In particular, the operation that you get using a three-point moduli problem of genus 0. If I choose S minus to be 2 and S plus to be 1, what I will get is something that looks like a multiplication. I take K0 of X squared, going into just K0 of X. It turns out that that multiplication, if I take into account all curve classes, is an associative multiplication. And that's called the quantum operation on K-theory, quantum multiplication on the K-theory tensor. Okay, and then if S plus is empty, then basically what I'm doing is I'm thinking, okay, I'm putting maybe some skyscraper shifts or some structure shifts or subvarieties, I'm putting them back, and then doing with the virtual shift to make it have something that looks like dimension 0, and then I'm pushing forward to just a point. But the case of a point is just an integer. And you should be thinking of that as kind of a count. I'm counting kind of, I'm pulling back, I'm putting some conditions on the markings, and the output is a count. And this is kind of just capturing a bit more general thing where I'm thinking of operations instead of count. Anyway, so this has a lot of nice properties. I'm not going to go into all of the properties that one needs. And the main goal of this talk is to generalize this to counting things in other contexts. The main context that I'm going to be interested in is when we replace X with BGLN. Any questions? That's kind of just the motivation.
Just a question. Is it a Frobenius algebra? So is it giving you a proper topological quantum theory?
I think, well, over some base, right? So here, I'm just doing it for beta. In order to define it, in general, what I would do is I would do a power series on curve classes in beta. So I would introduce some variables, power series of variables that is keeping track of the curve class. So it wouldn't be over just like, some field, or like, I guess in here, I could be thinking over Z or over Q. But it's going to be over something that is sometimes called an Novikov ring. So it's going to be something power series. And I think in that case, it's going to satisfy some of these variables. And the reason is because it has some nice gluing.
Yeah.
But I think more I mean, it's fairly rich. It gives you something that is called like a. But you can also push forward to MG bar and get something related to something that's called a core. Okay. All right. So so I want to count curves in BGLN, and just as a reminder, a morphism from a curve into BGLN is the same thing as a rank n vector bundle. So really what we're doing is we're counting nodal curves with rank n vector bundles. And we're trying to, in some sense, parameterize or like get a compact moduli space of rank n vector bundles on nodal curves. And the whole point is if you want gluing morphisms to be compatible or like to have a well-defined gluing morphism, we're not going to put any kind of stability on this. So we're going to work roughly with the stack of all vector bundles, but we're going to need to put some properties in order to cut down how big the stack is going to be. But over the locus of smooth curves, we're basically just going to work with the stack of all vector bundles. Okay.
Finite automorphisms?
Yeah, I mean, this is
You don't
pretty much
require.
never going to have finite.
Yeah, okay. So you forget about the.
Yeah, I mean, I could impose finite automorphisms if I like remove the central GM, but even then, I don't think it's.
Yes.
Yeah. I mean, that's not going to give me like compact. Okay, so let me be more precise. It turns out that this thing that I said, the finite automorphisms, is an open condition. So you could consider a stack of all morphisms from a pre-stable nodal curve into X in the previous setting. And then there's an open condition, this is called Kontsevich stability, that gives you a property. So what we want here, more precisely, is we want an open substack. I'm going to call it M bar G, and I'm going to do something weird here. In Kontsevich stability, or like in the moduli problem of stable maps, we don't distinguish between the inputs and the outputs. It turns out, and this was like a big headache for us for a while, that in order to get something reasonable here, the only way in which we could do it is by in the moduli problem itself, distinguish the inputs from the outputs. So here, the moduli problem doesn't care. All of the points play the same role, regardless of whether we were taking them as inputs and outputs. Here, I'm going to fix some number of negative markings. Those are going to be the inputs, and positive markings. Those are the outputs. And it's going to go into BTLN. And now, the curve class is roughly just telling me what's the degree of the vector bundle. And that's going to be inside of the stack of, I'm going to call it M pre-stable, G N plus P, VGLN, which is just a stack of all morphisms from a curve with M plus P many markings into VGLN. So it's at the degree of, well, let me not put it there. So that's just literally any nodal curve with some M plus P markings and a ranked vector bundle. And we want to define this stability. And of course, we want some desiderata. So in order to have a picture similar to this, we're going to need the following, such that there is a level line bundle left inside of the area of this moduli problem, such that the following hold. And maybe as a spoiler, so this line bundle is going to, over the locus of smooth curves, as I said, the stability is going to be nothing. We're just going to take, at least if the positive markings don't exist, the stability is going to be nothing. We just have the stack of all ranked vector bundles of degree B on the smooth curve. And then this line bundle is the line bundle that recovers Berlin's, the Berlin vector bundle over MG. When you push forward. So what do we want? We're going to have GNP bar BGLN. This is going to be, as I said, some positive markings and negative markings. I have a vector bundle. When I have this vector bundle, I can restrict to the markings, and I get just a vector bundle with the point. So I have a negative evaluation morphism, and this is just going to be BGLN P to the n, the number of negative markings. I have a positive evaluation morphism. It's going to be BGLN to the p. And I want the Fourier-Mukai transform to be well defined, which is very non-trivial in this case, because as I said, there's no stability. This morphism is not even of finite type. It's not quasi-compact, let alone proper. So for example, if I just consider the locus over where I'm like over a smooth curve, this is the stack of all vector bundles on the curve. And what do we want? We want that if I take a class in K0 of BGLN, by the way, this is just the representation ring of BGLN. In other words, this is just symmetric Laurent polynomials. So the main idea of this is we're trying to define quantum exotic operations on this representation ring of the algebraic group GLN. We pull back, so it's a concrete. We pull back under the positive evaluations with a K0 plus BP with tensor by some positive power. This is some positive power of this level line bundle, so A is going to be bigger than 0. And then we push forward, and this is where, so far everything is perfectly fine, but now we push forward. And we want this to be well defined and to land in finite, just coherent K theory of PGLM to the people. So we want some kind of properness, at least cohomologically, even though this morphism is horrible from the point of view. I mean, it's not even quasi compact. So that's what I mean by defining K-theoretic Jordan-Whitman theory. So you have some kind of quantum multiplication of this thing. Okay. And maybe the second thing is if we want something that looks like kind of not exactly the TQFT axioms, but something similar, we might want this class that we're using to be compatible with gluing morphisms. So that's the first desideratum. The second desideratum perhaps is, or second desideratum is we want gluing morphisms. I don't know, so I can take MG and so let me do this once. Such that this class of the line moduli is well defined. So it behaves well with respect to the gluing morphism. So if I take the level lambda log, this is just a box tensor. So I want this class that I'm using to do this thing to be compatible. And of course, yeah, I want something similar for oops, sorry, I made a big mistake here. And that's the whole point of this. Sorry for that. So the whole point of these gluing morphisms is I'm only going to be able to glue an output to an input. If I'm thinking of going output to input in this well-defined thing, the only thing that I'm going to be allowed to do is to glue an output marking to an input marking. I'm not allowed to, well, technically the gluing morphism that I said before is well-defined, but gluing morphisms between outputs are not well-defined. So it's better if I write it this way. The gluing morphism that I wrote before exists, but the one that I'm interested in is this one. So if I want something like composition of applying this should be functorial, I might want something like this. Take the output and I glue it to the input. Okay. So let me tell you what's the answer to this moduli question. Like, what is the stability that one needs to impose? So here's a definition. Okay. Rank in second law is the data of tuple C with n minus markings, P plus markings, and a ranking vector bundle on C. So right now I'm just telling you a morphism in this big stack of pre-stable curves mapping into VGLN. Just a nodal curve with some markings and a ranking vector bundle, such that the stabilization morphism so we have a stabilization morphism from the curve to the corresponding marked pre-stable point. Maybe I should say the marked stabilization morphism. So you just keep contracting all the rational curves that have less than 3 special points, and you contract until you get something that is like marked and marked stable. So the homomorphisms are finite, satisfies the following. And there's 3 conditions. The first condition is that this vector bundle is globally generated relative to this morphism. In other words, the co-unit of the usual push-forward, pull-back adjunction is surjective. The second one, something that I'm going to call concept stability, it says that the determinant of this vector bundle is relatively humble for the stabilization modes. And then the third one is that the push forward, and this is kind of the trickiest condition, originally due to Giesecker, and then in the work of Nagarash, that the push forward of E, that's a shift on the stabilization on that nodal curve, and this is pure of dimension 1. Or if you prefer, sometimes people call it torsion. It doesn't have any subshifts supported in dimensions. So, I keep forgetting about the plus markings. Sorry, it's because I usually give this talk without the positive markings, but I think I decided to give the talk with positive markings. So this is going to be E twisted but minus the positive markings. So that's the only place where the difference between positive and negative markings is evident.
The negative markings play no role, right?
No. I'm going to explain a bit why we're doing things this way. So in some sense, this is kind of like a variation of kind of a classical type of moduli problem. I would say the main novelty here is addressing these like positive marking evaluation morphisms, and then proving that that cohomology is finite.
But I guess that the last condition is only important if the positive markings are in some rational curve that you contract, right?
And then I don't expect this to this is just the simplest way of putting the conditions. I'm going to explain what this means right now. But let me just remark that all of this, this is open. This thing is open, surjectivity is open. B number is going to be open, and at this point, being pure of dimension 1, once you have the first condition, so a relative version of cohomology basis tells you that this thing is going to be flat in the family, and that purity is going to be an open condition. So this is pretty straightforwardly an open condition. It's an open substack of just a stack of all markers and fractions. Okay. Yeah, maybe let me state the main theorem, and then I'm going to explain what this moduli is after. But the main theorem is that the stack MPP bar VGLN D of Gieseker vector bundles of degree D, so I require that E has degree D, satisfies the two conditions. So I can say that this is finiteness of cohomology. That was the first condition that I wanted, that this push forward on K3 made sense, and gluing. In particular, one can define some K-theoretic remote with invariance of PGN this way. And for the rest of the talk, I just want to explain what this is. Okay. So we have a evaluation morphism, or we have a forgetful morphism, like this. Let me ignore the degree for now because I'm not going to need it. And we can go to MG M plus B bar. And I just take my curve with the minus markings, the plus markings, and E, and I can map it to its stabilization. Maybe I set 5. So in some sense, what you should be thinking about is we're kind of compactifying the moduli of vector bundles on the nodal markers by allowing some semi-stable, in this case not semi-stable if we have positive markings, but some models whose stabilization is that given curve. And this is a very classical idea. So how does this look like? So let me give you the simplest case. Let's consider n is equal to 1. So think of moduli vector bundles over stable vectors. Okay. So the first one is, let me tell you what it goes in n is equal to 1. And without markings, that's kind of a classical, as I said, classical compactification, going back to Capurnaso. So let's fix one of these stable curves. Let's fix the stabilization, and let's just assume there is something like this. And here we have like a minus marking, and here we're going to have a plus marking. And I guess this is over the stable curve, so this is going to be C stable. Then my question is, okay, over this element in here, what is the fiber? So here's what's going to happen. Over the minus marking, you're going to be an isomorphism. So this C is not going to alter anything around the minus marking. Over the node, you're allowed to sprout some bridge. So it's going to be a P1. And over the plus marking, you're allowed to sprout a rational tail. And the plus marking is going to be at the end of this P1.
You only have one P1, or you could have a...
So for n is equal to 1, I'm just going to have one P1. So let me explain to you a bit the conditions. So let's see. So, and we're going to have this morphism. So this is going to be the picture of C. And the vector bundle in here is going to be O1. Sorry, the line bundle in here is going to be O1, and it's going to be O1 there. So, okay, so what's going on with the conditions? Okay, so whatever I do, this C is going to be the same curve as what I started with, but with some trees of P1s, because they're supposed to have the same genus. Well, I forgot to say that, but yeah. I impose that the genus of the curve is going to be when I do the moduli. Okay, so let's try to think of what could happen if I have here a P1 and I have a line bundle. In this case, the condition about being relatively ample just means that this is going to be O1, n has to be bigger than or equal to 0. Global sections of this will generate it. And the relative ampleness means that it has to be actually n strictly bigger than 0. So for n is equal to 1, conditions 1 and 2, actually condition 2 already implies condition 1. So in principle, I could imagine that I could have any On for n positive. The problem is if I have On that is bigger than or equal to 2, then I can find a section of O2 that vanishes at 0 and at infinity at these two attaching points. I glue that section with the 0 section everywhere else. And then I can consider that as a section of the push forward that is supported at the node. And that's going to give me torsion. So that's going to contradict the push forward being pure of dimension 1. So this is forced to have O1. If I have a chain of P1s, then again I'm forced to have O1 and O1. But then I could take a section of O1 that vanishes at this point and then glue it non-trivially to another section that vanishes at the other point. So if I have a chain of two P1s, again, I get torsion. So that forces this thing to be a symmetric one. If I had something at this, marking, another P1, then again, because it's supposed to be relatively ample, it's supposed to be O1 for some positive thing. The same reason as what I was saying before forces this to be O1. But now I run into trouble because O1 has a section that just vanishes at a single point, and I can glue it everywhere else to 0. So I'm not allowed to sprout this. But here, remember that the condition is E, or in this case, I guess L, to the minus the positive markings having a torsion-free push forward. And now the main point is I'm allowed to have this because I have O1, but I'm twisting down by 1, and now the push forward is torsion-free. So that's why I'm allowed to have a P1 sprouting there. And the main thing that you should be thinking about is we're sprouting these P1s to compactify the modular vector bundles over the nodal curve. And then we're allowing to sprouting these P1s at the evaluation marking, at the output, in order to compactify the F plus. But we don't need to do anything with the F minus. And now, I can always glue an output to an input if I have another stable curve, and I have here a minus marking, and I don't know, I have a plus marking, and I have another curve in here with some line bundle. Maybe I don't have a P1 in here, and maybe I still sprout some P1 in here. Then I can glue these two curves. I can glue, as I said, the output marking, I can glue it to an input marking. So I can glue these two curves to get a bigger nodal curve, and this becomes a node. And now I glue this plus marking to the minus marking, and this becomes a bridge P1. Separating this node. So gluing works. As you see, I can't really glue plus with plus because I will get two P1s. But I can always glue plus with minus. And this is the simplest case of n is equal to 1. So when n gets bigger, the combinatorics get a bit more difficult. But it turns out that whatever condition I have, and it's some condition similar to this, I can always do a plus with a minus, and what I get is still satisfies whatever condition I have. Okay? So that's roughly the picture of n is equal to 1. Questions about this? Okay, good. All right, so at this point I can try to see a really rough idea of the geometry that comes into proving the things that I said, or I can see a bit more what happens in higher rank, and I can ignore concept stable maps that appear in the
Proof.
Okay.
I vote for proof.
Okay, so I mean, I'm not going to give you the proof, but I'm going to give you what I think is a cute idea that appears in the proof. Yeah. Or maybe I should say maybe a bit of slight motivation. So when p is equal to 0, then we have this moduli. Which I said is going to live over mg. Let me put both of them to be equal to 0. Right? So this is going to be a moduli of Giesecker bundles over mg bar. Over the stable locus, if you think about what I was doing, I'm not allowed, over the stable locus, there are no nodes, there are no markings, there's nothing that I can add, there's no p1s that I can add. So this is just the usual moduli of relative vector bundles of rank n on the universal curve. And then this line bundle that I call the level line bundle is actually just the determinant line bundle. So it's going to be, you take the universal line bundle, you direct sum with the tensor by the canonical of the curve, you take the derived push forward, and you take the determinant of that. So that's a power of what people generally would call the determinant line bundle. Here, if I take this level line bundle, which is the determinant line bundle, and I have over A, I have no inputs. I'm just taking a power of this and I'm pushing forward. So let me call this the stabilization coefficient. And I push forward. And this is already known that if I have the stack of all vector bundles of some fixed degree in here, even though it's not a finite type stack, actually derived global sections of this, well, this doesn't have higher cohomology, and the global sections of this is a finite dimension of the fibers and gives me a vector bundle in here. So the push forward of this is a vector bundle over the smooth locus. And this is what is usually called the Berlin bundle. And already the rank of this is given by this, I don't know if you've seen it, this Berlin formula. So this combination of special functions, sines and cosines are some special values. So already this case of 0, 0, and no insertions, the push forward of this is capturing something kind of interesting. And of course, our theorem says that there's a moduli theoretic compactification, and the push forward is a perfect complex. So all the cohomologies are still coherent. So it's an extension of this Berlin bundle. And something that I don't know is whether that push forward is actually a vector bundle. It's known that there's something called conformal blocks. There's like an extension using a logarithmic connection of this Berlin bundle to the third mg bar. So this is a possible candidate of a moduli theoretic interpretation of this extension. And you also have these gluing kind of ideas where you could try to prove things about this extension using moduli theoretic gluing.
Sorry, how did you get the level line bundle?
Yeah. So L, I'm just going to write it here. I said it, but I didn't want to. So this thing is going to be the following. I'm going to have my universal curve equipped with a line bundle over C over this moduli of. I mean, it doesn't matter if it's NP, it's the same thing always. And what I'm going to do is I'm going to take E universal. I'm going to direct some, let me call this morphism pi from C into the base. And I take this E universal, I'm going to direct some E universal times the relative canonical of this curve. I'm going to take the right push forward, and I'm going to take that's a perfect complex, and I'm going to take the determinant. So in some sense, over the locus of over the smooth locus, this is just the usual stack of vector bundles, and this is not that different from, let's say, taking a cohomology determinant of cohomology of endomorphisms of the universal graph. This numerically is the same. Okay, so let me give an idea of some geometry that arises. One idea of some of the things that arise in the proof. Okay, so the main point is one can interpret, and I think this is like a new approach, this kind of classical problem. One can interpret physical vector bundles as consecutive stable maps into a degenerate Grassmannian. So if you've seen this type of modular problem in Nagarase, Sadiri, or like Smith as a construction of the GIT modular space, generally the validity criterion of properness is a bit difficult. You do a bit of resolution of surfaces to get it, and you use very precise knowledge of the formations of torsion-free sheaves on an urban curve. But what I'm saying is, actually, the fact that this satisfies the relative existence of the relative criterion for properness is kind of formal and follows from this conservative maps into a degenerate Grassmannian. Okay, so let me stay with the case where there's no markings. And let me take again the approach, or like the kind of point of view, the perspective of starting with a stable curve and trying to describe what's the fiber of this. So let's start with like a stable curve. Here's the stable curve. And now I have the push forward. I'm going to have F, which is going to be a torsion-free sheet for a pure sheet of dimension 1, and this is supposed to be the push forward. So I have a morphism from this into stable curves with torsion-free sheets, where I just stabilize and I push forward the vector bundle. So this torsion-free sheet is going to have rank n. So it's going to have rank n genericity on the curve. Away from the node is literally a vector bundle of rank n. But because it's torsion-free, at the node, the rank is going to jump. It's going to have rank n plus k. And what we're trying to do is, we're trying to somehow modify the curve to transform this torsion-free sheet into a vector bundle. And here's the cheapest way of doing this. I can consider the quote scheme. Here's the universal way of doing this, the quote scheme of this torsion-free sheet. Here by quote scheme, I mean I'm considering just the identity morphism, so this is relative to a CST, and consider this sheet, and the T points over a CST scheme. This is just the set of vector bundle quotients of rank n. But what you should be thinking of this is just a relative Grassmannian over here. So if I take a point, I look at the fiber of F, and the fiber is just the Grassmannian of rank n quotients of this vector space. So away from the node, I have a vector space of dimension n, that's the fiber, and I'm looking at quotients of dimension n of a vector space of dimension n. Well, there's only one of those. So away from the node, this curve, or this quote scheme, is isomorphic to CST. But at the node, what we're doing is we're replacing this thing with a Grassmannian of rank n quotients of this n plus k dimensional space. So that's what this universal thing does, resolving this thing. And now, what is the easiest way of trying to resolve this torsion-free sheaf? Well, I can just join these 2 points where the Grassmannian attaches by a chain of rational curves. And what I'm going to get is I'm going to get a curve, which is the same stable curve as before, but now I sprout some rational P1s. And I have this morphism down, which is going to be the stabilization. By definition, here, this describes a quotient of this torsion-free sheaf. I pull back, and I have the quotient E. But remember that this torsion-free sheaf was supposed to be the pullback of the push-forward of E. So mapping to this Grassmannian is giving me a ranked vector bundle. And if I think that this push-forward is supposed to be the torsion-free sheaf, this map into the Grassmannian is telling me that this is globally generated. So that's condition 1. Now, this map is into a projective thing over the point. This is a projective scheme because it's projective, fibers Grassmannian over something that is projective. And I can require that this thing is conceived stable. And okay, if you're familiar with conceived stability, this just means that these P1s are not supposed to be contracted by that morphism. The easiest way of requiring that is I take an ample line bundle on the Grassmannian, I pull it back, and I require that this ample line bundle is positive on these P1s. If I have the Grassmannian, that has a universal quotient, and the ample line bundle on the Grassmannian, or one of the usual ample line bundles on the Grassmannian, is the determinant of this universal quotient. When I pull it back, I just get the determinant of the pullback of the universal quotient. And requiring conceived stability just means that this is supposed to be positive on these P1s, which is exactly the same thing as saying that it is pi-ample. And then the third condition is just saying that I have this morphism from the pullback of F into E. This was really an equality, but like it's not a priori clear that that's going to be an equality. When I push forward, I have a morphism from F push forward pullback F, and that's going to go to the push forward of E. And this condition, I'm going to require that this is an isomorphism, so that the push forward of E is the torsion-free sheaf that I started with. And then the main thing that, or one of the main inputs in the proof is thinking geometrically of this, to think about this as a projective problem over the moduli of torsion-free sheaves, because this is just conceived stable maps over some Grassmannian over the universal torsion-free sheaf on the moduli of torsion-free sheaves of stable curves, which is known to have, you can fill in families, so it's complete. Because conceived stability, you see that this moduli is also complete, and that's, I think, an easy proof of this like Gieseker or Caporaso type moduli being complete. I mean, in the Caporaso case, it's easy to see, but in higher rank, I think it's more difficult, and this is kind of like a free proof of that. With positive markings, I should say this is kind of like the easiest case. With positive markings is really the actual difficulty in the paper. So that's what we do. But I would say, yeah, maybe you can just, if you want to take something out of this talk, you can take this kind of geometric picture. So this is how you replace the moduli of torsion-free sheaves with the moduli of vector bundles and curve modifications.
Well, thank you very much for the very nice talk. I really, really enjoyed it. I was wondering, is it possible, so the motivation that you had, that you want to create a map from K0 of the input to K naught of the outputs. Can you do this derived instead of K naught of coherent sieves in the derived category of coherent sieves? Is it going to work?
We proved that the Fourier-Mukai transform, the thing that I did, is well defined, sends perfect complexes to perfect complexes. I mean, that's what we proved, and then you just take case theory.
Okay, perfect.
The actual result is that thing that I did maps
perfect complexes.
Maps perfect complexes to perfect complexes. So you do get, So this thing that I said you push for and you get a perfect complex, that's technically like part of this thing that I said. So in particular, you have any of these tautological classes that you get by pulling back short functors from the evaluation morphisms, like if you prefer, applying a short functor to like the restriction at some of the markings of the curve, and then you twist by this like the terminal line bundle, you push forward in this huge stack with no stability, and then when you get this, you always get a perfect complex, something that has bounded and coherent cosmology.
Right.
And the whole point of not imposing stability even over the smooth locus is because if you know about stability of vector bundles on other curves, any kind of stability that I can generally have that is completely general doesn't behave very nice with respect to gluing. If I have something that is stable on this curve and is stable on this curve and I try to glue, incomplete, like I run into like some annoyance of like exactly what conditions I need for gluing. So what we said is we just give up, take the entire stack, no stability, and just try to prove that the integral of the K3 class over that huge non-finite type stack works. And then gluing is well defined because you don't have anything to worry about.
Maybe you can give us a hint of what happens on the fiber rank case.
I mean, it's kind of combinatorial in nature. Kind of.
How
Maybe
many?
like
5 minutes?
Well, I'm a bit worried because I think like there was like some event. So like if people want to leave, they can leave, and I can just keep like talking. Yeah. But if anyone wants to leave, you're welcome. It's okay. I'm not gonna.
It's just food.
Okay. So I mean, it's actually a combinatorial condition. So if you're happy with Caporasso's thing, it's also kind of a combinatorial. So let me say, let me do rank 2. And if I tell you what happens in rank 2, then you basically know what happens at any time. So so let me start with the stable curve down here. No markings. Let's just see what happens at the node. And let's say n is equal to 2. Okay. Then I'm going to have a chain of P1s in here. In principle, a lot, but what's going to happen is it's going to be at most 2 P1s. So let me draw to you all of the possibilities. So one possibility is there's a single P1. Then any Rankine vector bundle on this, any rank 2 vector bundle on this P1 is just a direct sum of ONs. The vector bundle is going to look either O direct sum O1 or O1 direct sum O1. So the main point is I cannot really have O2s because I run into the problem that I said before. And I need the determinant to be positive, so at least I need an O1 in here. Or I can have 2 chains a single chain of 2 P1s. And now it's a fact that any vector bundle on a chain of P1s also splits as a direct sum of line bundles. And they're going to be of the form O N1 N2 direct sum O N1 N2. Where by this I mean it's a line bundle that restricts to ON1 on the first P1 and ON2 on the second P1. And by the same thing that I was saying before, I cannot have 0, 1, 1, because that would mean that I could have a section of 01 that vanishes at this point, and I glue it non-trivially to like a section that vanishes at this point, and I get torsion. So I cannot have 0, 1, 1. I can only have 0, 0, 1, which means that it's trivial in here and a no one in here. But if I want the determinant to be ample, this second one should at least have a 1 in this first component. So I should put a 1 in here, and then a 0 in here. And basically, if you understand this, then you understand how it works all the time. How it looks like is I have a chain of P1s. The vector bundle is going to split as a direct sum of O with some commas. And all of these line bundles is just going to be 0, 0, 0, 0. There's a 1 somewhere in the chains, and then 0, 0, 0, 0. And some of them might be trivial. So the line bundle restricted to the chain of P1s, this contracted chain of P1s, let me call it chain, it's generally going to be of this form. It's, let me say it's like some copies of the trivial line bundle to the A, and then there's going to be some copies of O, yeah, so I of O, where it's zeros everywhere except 1 at some spot, and I'm going to say that I use the Kronecker delta function, so O delta ij, and there's going to be some copies of this. And the requirement is that for all I need at least one of these to be non-trivial. So bi is bigger than c. And this just comes from like simple-minded considerations of when the push forward is not going to be torsion-free. And this is how it looks like. And now, why is the chain bounded? Well, if I want at least one for each element of the chain, this ranges over the length of the chain. So if the length of the chain is length L, then I have for each spot, I have like a 1 in one of them. If I want a vector bundle of rank n, and I want something such that every element of the chain at least has one bi in here, obviously the length of the chain is going to be at most the rank of the vector bundle. So this bounds the number of things that I can have in the chain. So the chain for rank n is going to be at most rank at most length n. And for length n, basically what you're going to get for the maximal length is just a permutation, so kind of like direct sum of all the possible things where I put a 1 as one single element of the chain. In some sense, for that maximal length, up to isomorphism, there's going to be only one restriction of the vector bundle. Just run over all possible permutations of this O1. And then in the middle, it's a bit more complicated.
Great. Thank you very much. Well, let's thank the speaker again.